so it's taking a bit of a time. So yeah, this is it. So double precision display mesh. So depending on your computer, you could use it for here. Okay, so transients, use transients for this case. The model, viscous model, I will use the K epsilon, depending on what you want to use, realizable. Okay, then for the materials, make it constant. Yeah, you could make it constant or not, depending on you. For a better solution, make it Sutherland. To make this ideal gas. Then you don't change grades. Then you close. So the cell zone is fluid, so as you could see. So under here, this one will specify the rotation of the sphere. So we go here, edit, so mesh motion, the rotating axis is about X. Because depending on how you actually want your ball to rotate, if you want your ball, since my flow, I assume my flow is going this way, so I just want my ball to rotate in a way that is perpendicular to the flow, so it rotates about X axis. So I'll just put 1 here and this kept at 0. And since all my drawing starts from the origin, so basically I have nothing to put here. So your speed, depending on what you want. If you want to change it to RPM, because this is in rad per second, so you could just go to the unit here under angular velocity, say RPM, then close. So here it says RPM, so I could say how many revolutions do I want per minute. Let's say I want 60, or let's say 30. So yeah, depending on what you want. Apply, close. So we'll go to the boundary conditions. So basically what we're concerned with is the inlet, outlets, and so for this, keep the temperature at 200 depending on what you want. So could say magnitude and direction. So let's say velocity of 15 or 10, velocity of 10. Yeah, going towards the x. Now look at, it's going towards the negative x direction. As you could see from here, it's going this direction, and that's the negative x. So we put minus here. Keep all the other things constant. Close. For the outlet, is a pressure outlet basically, so you could change this. So I'll just use, there's no velocity outlet, so I'll use velocity inlet basically, but I'll be editing what is inside, so it won't really have much problem. So that's what I did the previous time. I'll do it again. Velocity is 10, and it's also towards the negative, so the flow goes one direction in negative x direction, and apply, close. Okay, so we go to, before we start, we go to calculation activity. Yeah, so if we would like to save our results, because it's a transient it's not steady state we're using a transient solution, so we need to save our results per time, so we could see what's happening at various times. So we could just create particle history. No, solution data. So under solution data, change this to, then you could select all this, and time step. So you could say for every time step, I plan using 100 time steps. So let's say for every 10 time step. Yeah, you could change this, you could make it lower to capture more of what is going on. So let's say 5. So 5 time steps. So okay, we go to initialize, go to hybrid initialization, initialize, surface penetrated. Let me look at this once more. I think we're good here. So we've initialized, then want to run calculation. So number of steps, could say 100. Time step size, could say 0.05. So basically, yeah, calculation you could increase it or not, but I'll use a 5 iteration per time step, and I'll calculate. This will take a bit of a time, so we'll come back to this. Yeah, so we're back. Calculation complete. So this is how my calculation look like. So from here we'll go to the post-processing, which is the results. So here we could just select results from here. And open this. Take a bit of a time. Yeah, so we go to file, load results. It's taking a bit of time. So here, so we could do a number of things. We could look at the velocity changes. I've just created a plane, an XY plane. I'm going to do a contour. Create a contour, say 100. Let's look at all domains, location, plane, and could look at the pressure. Let's look at the pressure. So basically this is how the pressure looks like. Let's look at the velocity. So this is how the velocity change. So if you look at this closely, you look at this. So this is part of the fluid, which is the second sphere we drew. So this is our main focus, which is the ball of 10 centimeters. So you could see here, this is how the velocity has sat 1.5 seconds. This is how it looks like. we could run a simulation. Let me see. So we could go here. So you see at at the at the fifth time step, this is how it looks like. If you increase it, you see changes. Then I think after a while, like we could see here, like maybe let's say at 8 iteration, that's like 30 times step, that's 30 times 1 times 15, that's about 0.045 seconds. It basically becomes steady. So yeah, I'll just run a simulation for that. Let me repeat it for like 5 times, or let's say 7 times. Save file, save it at desktop. MP4. Depending on what you want, you could go to more options and could make the quality high. Frame 60. So I'm going to play it now. And to take a bit of a time, so we'll come back to show you the simulation results. Okay, one way to notice the rotation of the ball is if we look at the vector. So we go here, we click OK, then if you click OK, you get to something like here. So one way to look at it is to look at each axis, the planes, the XY plane, the XZ plane, the YZ plane, and to look at the vector around it. You really appreciate the rotation. You really observe the rotation. So here, let's go to the plane. So the plane here is in the plane is in XY. So the vector is in the plane, then say the vortex. So let's look at how it is. Let me close the contour and apply the on the plane and apply sorry, vortex. So here we see how we see the velocity, we see how it goes. So it rotates about the x direction. So we see it goes up here, it comes down here. Now we're going to look at the xz direction. So we'll go back to plane, we change this to xz, then we apply. So look at this. See, there's a difference between this and what we initially saw. So here also, since it's rotating about x-axis, it pushes it to this side of the plane, As you could see, look at this other end. This end is, there's not much of a velocity there because it's rotating about that direction. You could also observe same thing looking at YZ. We apply. So this for YZ, let's see. So say for YZ, it's rotating about the x-axis. So you see how it's equally distributed. The velocity goes, since it's rotating around, so it pushes it everywhere around here, unlike the previous two. So here, that's what I have for you. You play around the animation. Yeah, so thank you for watching.